Hi guys, so last time I showed you how to connect this serial transmit circuit that I'd built up to a 6502 computer, and we had that connected up and we had some characters appearing on the PC's console when the code in the 6502 computer sent characters to the transmit circuit. Now my intention with this circuit was only to get that far really, just as a mechanism for getting character data out of the 6502 computer and into a PC, but I couldn't really help myself at that point. It wasn't too hard to design this circuit, so I thought it might be interesting to design a receive circuit as well to go with it. So that's what I went away and did, and that's what I'd like to show you today. So the general principles of this circuit were to keep things simple. I didn't want a lot of configuration stuff to be done by this computer onto the serial device. I wanted it to just be plug and play and off it goes. So it doesn't require any configuration at all. It presents itself as a transmit data port. It's connected to the data bus, so when the CPU writes a byte of data to that address, it transmits that character. And there's also a readable register which informs the computer when the device is busy, so that the computer can wait until it's not busy before sending the next character. Now I designed the read circuit to work in a similar way. So the read circuit is going to provide a readable register for the computer to read back the character that has been received, and it's also going to need to provide another bit of data here to inform the computer when there is a character that can be read. And in addition to all of that, I'm going to set up an interrupt output from this circuit so that it can interrupt the CPU whenever a character arrives on the read circuit, and also after transmitting a character on the transmit circuit, because that'll allow us to write asynchronous code on the computer to automatically send characters and receive characters when they're available into buffers in memory. So with all that said, let's have a look at the schematic for the receive circuit. So here's the full schematic I designed for the serial interface. Along the top row is the same circuit that we've already built for the transmit side of things, including this flip-flop which provided the transmit data register empty signal, and the other thing which I've moved from up here is the little bus transceiver, the 4-bit bus transceiver, which was mapping the transmit data register empty signal through to the CPU's data bus. So those components, this one down here and all of that top row, are already present in the circuit that's already been built. So the receive side of things is really just this bottom row. So let's have a look at what's going on there. To begin with, I showed these diagrams before of the format of serial signals, so we can have another look at those quickly now to see what we're going to need to do in order to detect and receive a byte. The serial byte always starts with a start bit, which is a 1-bit duration low on the transmission line, and that's followed by 8 data bits of whatever value is the byte that's being sent, and then the line goes high again, at least for 1-bit duration, but potentially for as long as it likes if there's no more data to be sent. And again, we're using TTL level voltages here, not RS-232 level ones, so 0 volts is space and 5 volts is mark. So in order to receive data, this is all coming asynchronously. There's no clock signal that we're sending out, so we need to be on the lookout for this start bit so that we know when to start sampling the data. And it's really this transition down that we're looking for, because after that transition down we know that in 1 baud duration's time we're expecting a transition to the level for the first data bit that we want to read, and this is the least significant bit of the byte being sent. In order to sample this accurately, what we really want to do is wait for 1.5 bit periods after that falling edge, and then sample about here to tell whether this bit's a 0 or a 1. Then after that we want to wait for an entire bit period between bits, so we're sampling in the center of every bit, as close as we can to that anyway. And then when we get to the end, we're going to wait that duration again, and we're going to sample again, and we're going to make sure that that's a 1. If that's not a 1 that we read at the very end, then that's called a framing error, and it means that we're out of sync with the asynchronous stream that's being sent to us. We're not interpreting it correctly, because every byte that gets properly sent should have a 0 here and then a 1 this duration afterwards. So if we miss that, then we're probably not properly in sync with the data stream. So detecting framing errors, that's how it's done, but I'm not sure. I don't think I'm going to bother with it as a first pass, but potentially that's how you would detect a framing error. So what we need to do is sample at a certain time after this falling edge, and the easiest way to time things I find is to use some form of clock signal that's fast enough and count a certain number of cycles of that clock signal. So I've already said that we're using a 4 megahertz I/O clock in the computer that we're connecting this to, so that's a nice frequency to be using. I think that's about right for what we need here. So what we're going to be doing is all the way during this period we're going to be sampling once every 4 megahertz, looking out for this downward transition on the received data line, and when we find it we're going to reset a counter, and it's going to count down from however many 4 megahertz ticks it is until the middle of this bit, and that's going to depend on the baud rate. We already calculated, I think, for the transmit circuit that 1 bit duration is 35 ticks of that counter, so we had a 40103 down counter that was counting down from 34 through to and including 0 to count 35 durations to get there. So based on that, I'm expecting to have to add another 17 or so onto that, so this will probably be 52, is that correct? 35 plus 17. So we might want to set 51 and then count down from there. I can't remember exactly what I did, but we can check in a minute. After that, we need to wait an entire bit period before the next bit is sampled, so that will be 35 ticks from that point on, so we'll have to reset the counter to 34 at that point so it counts down correctly to the value to the point we want to sample over here. And from that point on it's just going to be counting down from 34 through 0 every time we go to the next bit. In addition to that, we need to count how many bits we're doing so that we know when we've finished the byte, and again I think that's another 40103 down counter that's going to take care of that for us. And finally, of course, we need to actually capture the bits and have them stored ready to send back to the CPU once the entire byte has been received. So we're going to need a serial in, parallel out shift register to capture all these bits. So let's have a closer look at the circuit and we can find those main components in it. Over here on the left I have this flip-flop, which is whether the receive circuit's active or not. I wrote RD for read there, it should really be RX for receive, I think. Anyway, this flip-flop says whether we're actively reading a byte at the moment. So in the idle state, this flip-flop is going to be in the off state. But the receive data line comes in here, and whenever this received data line is low, it's going to set this flip-flop, which is going to force us into the active state, and the transition of this flip-flop from inactive to active is what's going to mark the start of the byte for us. This 40103 down counter over here is counting down from specific values here, and I'll talk a bit more about that configuration in a moment because it's quite complex. It's counting at the clock rate, the CPU clock I've marked it as here. It's actually the I/O clock in my computer, which is 4 megahertz. The tick enable is permanently low. I didn't put ground on there because there's a bit of a lack of space in the schematic editor, but that's held low so that it always ticks. We also have the parallel enable and parallel load pins connected through in various ways. Master reset is held high so that it never resets. It always ticks. This is the preset value it will count from, and what will happen is it will send a downwards pulse on pin 14 after that number of ticks, and that forms the read clock, which causes the rest of the circuit to read a bit. So what's going on with the parallel enable and parallel load signals? Well, parallel load is an asynchronous signal. Anytime this is low, this counter chip will read the value on the input here and set its internal counter to that value. Whereas parallel enable is a synchronous reset signal, so when that's low, nothing happens immediately, but on the next tick, on the next upwards pulse on CP, the counter will read the value from over here. So I'm using both of these to reset the counter in different situations. In particular, when the circuit is in the idle state and this U6B flip-flop is inactive, i.e. low, this read active signal is low, and that goes into the parallel load, and that means while the circuit's idle, this is continually resetting itself to the value it sees on these pins. So what's going on with this weird connection hookup we have here? Well, the point is, as I mentioned earlier, we need this counter to count down from two different values at different times. When the start bit is first detected, we need this counter to count down for 1.5 bits duration, whereas After that point, when we're already in the middle of reading a byte, we want this counter to count down from only 1 bit's duration. So in order to do that, we're using the output of the read act flip-flop, both directions of it, to control some of the counter preset bits. And that means that when this flip-flop is off, any bits here that are held to VCC are obviously set, and any bits here that are held to ground are obviously not set. That goes either way. But when this flip-flop is off, all the bits that are connected to RD act are going to be low as well, and all the bits that are connected to the opposite of RD act are going to be high. When the flip-flop is on, those two are going to kind of swap places. So looking at this another way around, for each bit of the values that we want to load, if the bit is set both in 1.5 bit periods and in 1 bit period, then we want that bit to always be set, and we connect it straight to VCC like I've done here for bit 2. If the bit is clear in both those scenarios, then we want it to always be clear, so we connect it to ground, and that's the case for bits 0, 4 and 5 here. The remaining bits are set in one but not the other of those two scenarios, and depending which scenario they're set in, we connect it either to the positive or inverted output from the flip-flop. I think the actual number I've programmed in here isn't correct, just looking at it, because it looks like when the flip-flop's off, we're going to get 0, 1, 0, 0, 0, 1, 0, 0, right? Oh no, we're going to get 0, 1, 0, 0, 0, 1, 1, 0, and that seems to be 70. So that's going to have a period of 71 because we have to include 0 as well, and 71 4 megahertz ticks is not the correct value for waiting from the start of the start bit to the middle of bit 0. I think I said earlier it should be 52 or so. So ideally we should be programming this to be 52 when this flip-flop is off and 34 when this flip-flop is on. Anyway, that's by the by. I will have fixed that in the actual circuit I built on the breadboard, so we can have a look at what value is actually programmed in there later. Anyway, by that mechanism, this flip-flop and counter combination will detect the start of the byte being sent, and it will time pulses on this output here, read clock, to occur during the centers of all of the bits of the data of the byte, not including the start bit, and also during the center of the stop bit. So that's pretty neat that just those two things together can do that. Moving on, we have another 40103, and I mentioned this one before as well. The purpose of this one is to count the pulses coming out of here and tell us when to stop when we've reached the end of the byte. So this is counting down from 8. The first pulse here will come at the center of bit 0, so after 8 pulses we'll be at the center of the stop bit, I suppose. Is that correct? I think that's right. So I guess this times until just after the stop bit. I'm not totally sure. So actually, sorry, I got that wrong. This will reach 0 at the center of the stop bit, and when this reaches 0, terminal count will go low for just 1 bit duration at that point. When it gets ticked again, terminal count will go high again. That generates this read stop signal, which is active low, and looks like that's feeding back round. That's feeding back round to turn off this flip-flop in sync with the next clock pulse. So that means that the read active signal stays high until the end of the stop bit, I suppose. Looking further to the right then, this is the 74HC595. That's a serial input, parallel output shift register, and what this is doing is it's picking up the read clocks that were coming from the first 40103, and every time one of those comes in, it samples the state of the read data line and shifts all its bits along one. Now this chip has a built-in storage register, so the shift register inside it isn't immediately presented out to the CPU's data bus. We get to choose when the storage register is updated from the shift register, and that's actually really handy. We do that with our clock here, and we do that at the rising edge of the inverted active signal. So when the receiving circuit has finished reading a byte, this signal will rise because read active becomes false, and that will cause the shift register here to copy the shift register content into the storage register content. In addition, the outputs here are tri-state. They're on the CPU data bus. We don't want them to be driven all the time. We only want to drive them when the CPU is trying to read the data. So the output enable pin is connected to the read receive data register signal here, and that will come from another one of those decoded I/O selectors that I showed last time. Other than that, we just have a bunch of flip-flops for housekeeping. This one down here is clocked by the end of the byte, and it just sets a flag saying the received data register is full. So when that's clocked by the end of the byte, it sets the flip-flop because the VCC connection to the data pin here. Receive data register full is very much like transmit data register empty was on the transmit circuit. This is the signal that tells the CPU that there is a byte of data waiting to be read, and reading from the receive data register will clear this flip-flop because we've read the byte. In addition, there's another one here. This one's called receive overflow, and similarly to this one over here, that's also clocked at the end of the byte. What it's doing is it's snapshotting the state of received data register full at the end of each byte. So after a byte is received, if the received data register was already full, then we've actually lost some data there because we've overwritten a byte with the next byte. The CPU didn't have time to read the previous byte. This is an error state that I've made this kind of preserve, and it stays set for quite a long time here. That's actually being reset by a read of the status register. So that will stay set until we actually read it back, and then it will clear that overflow flag. This is obviously optional to process. The circuit will work fine without it, but it will flag problems where the computer is not keeping up with the data coming in quickly enough. I would say that the storage register is actually really handy here, because what that means is that after a byte comes in, we have the whole duration of the transmission of the next byte to read that byte out again. It's not going to get overwritten until the end of the next byte, so that gives the CPU quite a large window to actually come in and read that data. But in order to make sure the CPU is actually reading that data at the right time, that's why I wanted to hook up an interrupt. So we can make this work with polling, but we might as well also set up an interrupt so that the CPU gets notified more proactively when these things happen. So that's what this flip-flop here is doing. This flip-flop takes the TX stop signal from the transmit circuit. That's the one which gets fired at the end of a transmitted byte. That will set this flip-flop down here, and it will set the IRQ output here, which can connect straight to the CPU's IRQ pin. Actually, it's the inverted one you want for that, really. But yeah, that's suitable for connection straight to the CPU then. We also set this flip-flop on a rising edge of receive data register full. I think that's sufficient. It means it's not set all the time whenever the receive data register is full, but on the rising edge of it, it will set this. And the IRQ state is also cleared by reading the status register. This isn't ideal, it's not a perfect way of doing it, but I wanted some way of clearing the IRQ state without actually consuming the data. So the normal way of clearing the IRQ state is, of course, to send more data if it was a transmit completion, or to read the data out of the received data register if it was a receive condition. But it's possible, particularly in the transmit case, that you don't have any more data to send, and in that case you want to be able to cancel the interrupt without actually sending another byte. And in that case, that's why reading the status register will cause that. It may have been smarter to pick writing to the status register for that one, just so that we can peek the state of the status register without actually changing it. And I think similarly down here, it's possible that this flip-flop should be reset by writing the status register, not by reading it. But that's a possible change you can make. It's not a big deal. I think it works either way. The transceiver over here is the same as I showed in the last circuit. It has the transmit data register empty signal being passed through to bit 7 of the CPU's data bus. The receive data register full signal is also being passed through now on bit 6. I mentioned the bit instruction being good for reading the top 2 bits of a register like this, so that's why RDRF is on bit 6, because that's also a handy one to be able to read very easily from the 6502 side. We also have the receive overflow signal is available here on bit 5. Like I said, you could just ignore that one and not use it. bit 0 here, sorry, bit 4 here, I have just wired high. I haven't marked it on the diagram properly, but I think I just didn't have anything interesting to put on that one yet. One option might be to connect it to IRQ, for example, so then the CPU could actually proactively ask whether there was an interrupt waiting, but that's a bit weird because, I don't know, it's going to get cleared as soon as you read the register and stuff. It's a possibility. Haven't really thought about that one in detail. Anyway, that's the run through of the new parts of the circuit for receiving serial data. It's very similar in principle to the way the transmit circuit at the top works. So I have a little bit of a correction here. After recording that walkthrough over how this schematic was put together, I actually went back and looked at the circuit that I built on the breadboard, and it turned out I actually had some bugs in that circuit when I first constructed it, and I fixed the circuit on the breadboard but didn't update this schematic. So I've come back to give a little errata list or correction to the explanation I gave previously. Now, the key things that differ are the way this stop signal works. Partly how it affects this flip-flop over here, also partly how the RD ACT signal drives the 595 here. I think what happened was the way I'd originally put the circuit together, it's possible that it was stopping too early or too late or something like that. I can't remember the exact details, but there must have been an issue with the timing of that stop signal, and I don't recall the details, I'm afraid. The change I made to the circuit to correct that, though, one thing I did was actually changing the count value here to be 9 instead of 8. So I think what I probably had previously was it was probably triggering all sorts of things like the receive data register ready signal too early. So this is now 9 instead of 8, so this is going to happen slightly later. So the next change was the activation signal into the register clock for the 595. Now this is the signal which causes it to copy the shift register content into the storage register. I had that down as RD ACT originally. Clearly that didn't work properly. What I did instead in the end was taking an inverter from this stop signal. I'm not sure where I should put this. I'll put it there. It's not very tidy, I'm afraid, but I actually passed an inverted version of that stop signal in here in the end instead, and this path going back to the flip-flop, I also changed that to come through a second inverter. So it's going through both inverters. Oh, this is getting really messy now, sorry about that. Let's move that over a bit. We can tidy that up as well. So this counter is going to count one more cycle. I inverted the stop signal to drive the shift register, and I inverted it again to drive this flip-flop. I think that was the main changes I made there. Another thing I did was take the reset pin of this flip-flop and actually wire it to the CPU's reset pin, so that during the power on reset the flip-flop initializes in the inactive state, so it doesn't initialize thinking we're in the middle of a byte. But yeah, I think that's the main changes, so hopefully that was all. So code-wise, here's the program that I wrote to test the serial output. So let's make another version of this for testing serial input. Just write a copy, and we'll make this serial input and output test program. So we have the transmit data register on FF60, the serial status register on FF50, so we can put the receive data register on FF40 based on where we connected it on the breadboard. And what else are we going to want to do here? Well, we might as well leave it printing A and Z. We don't need this loop I stuck in last time to just print Z's forever, so we'll get rid of some of that. Instead, what we're going to do is we're going to define a buffer. That can be at, it doesn't really matter where we put it. we can put it at 1000, let's say, and we're going to have a 0-page buffer pointer. Actually, we might not need that. We'll see whether we need that or not. Actually, before we go further, let's just make a print char routine, which can wait for the transmit data register to be empty. I think it was BPL I wanted here, and then store the accumulator in the serial transmit data register. So this will print a character to the serial output, the character coming in the accumulator. And this is where it's handy that the bit instruction doesn't corrupt any registers in doing its work. We can use these two instructions here to wait for the bit to be set without having to use any registers in the process. So the data that comes into this function in the A register is there and ready to go, ready to get stored. And we can also, I guess, define a read char function, which is going to work much the same way. We're going to bit the serial status register, and instead of BPL and BMI here, the read data register full flag is in bit 6 of the status register, so that's going to set or clear the overflow flag in the CPU, and we want to know when it is full, which is when the flag is set. So if the overflow flag is clear, we want to go back to read char now. So that will wait for there to be a character to read, and then we can load the accumulator from the serial receive data register and return. So again, very simple. Using the top 2 bits of the status register here makes life really easy. We don't need to save any registers or anything like that. We can just use bit and branch and we're done. So now we have these user-friendly routines for printing and receiving characters. I can come back up here where I loaded the Z and JSR to print char, and it will wait for the A to finish getting sent and then print the Z. Oh, one more thing I ought to do here, I guess, is also store it on the debug port, just for the sake of debugging. We're going to have the debug port showing the last character that was printed. So we'll print an A, we'll print a Z, and then what I want to do is go into a loop, and we're going to do this loop forever. And inside this loop we're going to load X with 0, let's use X, and then we're going to have an inner loop, for want of a better word. What I want to do is I want to read characters from the serial port, and every time I read a character I'm going to echo it back again. So we're going to call print char after read char, and if the character was a line feed, then a whole line of input has been entered, and what I want to do in that case is print a couple of blank lines and then print back the entire line that the user typed. So we should end up with a kind of double echo thing. You're going to type a line of text and hit enter, and then the 652 computer will send the entire line back again, and the user will see a copy of what they typed. So let's, inside this inner loop, we're going to JSR to read char to read a character. That's going to come back in the accumulator. I'm going to compare that with the line feed character, so the carriage return character. I'm going to branch of equal to line done. So anything else other than a carriage return that gets typed, what we're going to do is we're going to store that in buffer plus X. We're going to increment X, and if it's not 0, we're going to go back to inner loop. So if X was 0, then the line has actually overflowed the buffer, and I don't have a good way of indicating that to the coming up code. So I'm just going to decrease X again in that case. It's a bit naff. We're going to throw away a character there. It doesn't really matter just for the sake of this example. So this is going to be the line done routine. We're going to fall, when the buffer gets full, we're just going to fall through into the line done routine, and X will be set to 255 in that case now. So X is 255. Let's load Y with 0 now, and we're going to count up in Y and down in X until X hits 0. Actually, that means we were fine here. No, we weren't. if the user didn't type any characters, then we have a problem here. I'm just going to test for that here. So y is going to count up from 0 until it reaches x, but rather than comparing y against x, which you can't do on a 6502, I'm just going to decrement x until that also reaches 0. So let's go ahead with that. So before we do that, actually, let's print a line feed and two carriage returns, and let's enclose the user's text in quotes as well while we print it back. Partly because we can, but partly because making these kinds of distinctions makes it a little bit easier for debugging purposes to really convince ourselves that the serial data receive and transmit are working as expected. We should see things like the quotes being exactly on the ends of the string, no junk spaces or whatever in between. There's a lot of ways you can get this stuff wrong, and printing these sentinel characters, as you might call them, can be helpful. So, good thing to do. So I've loaded y with 0, we're going to have a line done loop. Actually, we'll call it echo loop because it's echoing the line back. What we're going to do here is load a with buffer comma y this time, and print that, and then we're going to decrease y and increase x, and if x is not, oh hang on, sorry, wrong way around. We're going to increase y, decrease x, and if x is not 0, then we are going to loop back to echo loop. If x was 0, then we're done, and what we want to do then is load another quote character and print it. Let's do another line feed and two carriage returns. I should almost have a routine for that, I think, and then we can branch back to the main loop. I think that's good. So yeah, I think that's good for a test program. Let's see how that goes. So another addendum here, as is often the case, unfortunately. While debugging the circuit, I've discovered I made some errors in the code, so I thought I'd put a little addendum in here to correct those errors rather than go back and forth in the scenes in the video. I thought it might make more sense this way around. The character code I should have been looking for here for end of line was 10 rather than 13. That's just what my terminal's sending through for the enter key. So I've corrected that here to 10. I had forgotten to actually print the character that was typed from the console, so there would have been no echo, so I've added a JSR to print char in here as well before storing the character in the buffer. And this no characters routine, again I forgot to put the thing in, so the label is now declared down here. So when there are no characters in the buffer, it should just print a couple of new lines and then branch around again. So yeah, those were the errata for the code, but that should be good now. So let's see it in action. Right, here's the new circuit all wired through to the rest of the circuit here. The main wires here are going to the decoding logic up here. I've also got some rather long orange and black wires here which are going to a spare inverter on the main circuit board, and that's for the additional inverters that I pointed out in the schematic that I forgot about the first time round. So that's actually not down here at the moment, that's all sharing one of the ones up there. The IRQ is connected through to the CPU. Our code's not using that yet, but it should be working fine. And I've connected the transmit pin from the FTDI through to the resistor network here, and that goes back to the received data signal on the serial circuit. So otherwise this is the circuit which was in the schematic with the corrections I already mentioned, and we have the terminal on screen so you can see what's going on. Let's turn it on and see what happens. So that doesn't look quite right, we've got some junk on the terminal there. Let's give it a reset and see whether that works any better. And yeah, that looks better, that's got AZ on it now. I don't know exactly what happened there, it may have been some glitches on the transmit data line or something like that during the power on. maybe it's due to my power distribution not being great. I'm not sure about that. Maybe that's something to debug later, but it seems to be working after a reset, so let's try typing some characters and see what happens. And yeah, the LEDs over there all changed, so I think that came through on the terminal. So I'll press enter, and yeah, the code seemed to work there. We've got a blank line printed, and then the thing we typed is returned in quotes. So yeah, that looks pretty good. Looks like the serial is working in both directions now. There may be some glitchy things to debug there. It looks like it didn't quite behave correctly on initial power up. We could try that again and see what happens now. And that is looking a bit better this time round. There was some junk printed when I turned it off. So that time it printed a P when I turned it off. And turn it on again. Yeah, just AZ that time. Now turn it off. And nothing that time. It is something I am observing. When the power goes off here, sometimes odd characters seem to get sent through to the PC. In this case, the blue light's not on here, so that tends to be a good sign, but I'm not sure exactly what that's about. Probably something to do with the resistor network not being great. But yeah, this is functional. Like I said, there may be a couple of glitchy things to debug here, but it is mostly working. So, result. One thing remaining for this particularly that would be good is making it not use 3 of the I/O slots up here. Really it should have its own little decoder on it, so we could do that in another video maybe. But mostly I think we're probably done with this now, and probably for the next video I can give a deeper dive into what's going on with the rest of this computer, how that works, why it was designed the way it is. Maybe a build guide if anyone's interested in that, either for the breadboard or the PCB version as well, if you're interested in that. Happy to show all the design files for that. See you next time.